Okay, if not yet, we will stick to standard materials. Lead based materials can act as a large infrared sensors. So now you can see the problem here. The more is the wavelength, is difficult to find simple materials. Why the band gap is there, we can discuss this in a later lesson. But for the time being, at least in near infrared, we have got a lot of material which we can use. In your table, you would have seen a large number of material which have got this band gap in this 1.59 to 0.4 electron volt regions. And people often divide this near infrared also in different bands. It's not just one big band. So you'll have sensors around 1 micrometer, 2 micrometer, and so on and so forth. Okay? So let's start looking at the type of devices which are made here and what are the things which is required. Now yesterday we talked about resolution. Now for these sensors, there are two things which are of interest to us. One is the temperature resolution. If my temperature is changing by X, what's my signal changing? That's fair enough. The other is spatial resolution. Remember, when we take cameras, we put large number of pixels and we call it resolution because this then determines what's the smallest distance in space I am taking a picture of. Right? More pixels, the area, I'm taking the same picture with more pixels, which means each space is denoted by higher spatial resolution. Now historically, IR cameras have lagged significantly behind visible cameras on their spatial resolution. Say you can get a 100 megapixel visible camera, but 100 megapixel IR camera is very difficult. Even few megapixel IR cameras are difficult to get. Unless of course you are a military contractor and you are making just one IR camera for one particular thing and you can charge a couple of million euros for it. Okay? So spatially speaking, IR cameras are still lagging behind their visible counterparts. By the way, can somebody figure out what's cadmium based materials band gap? Cadmium, indium telluride for that matter? That's another nice material to use for IR sensors, but anyway. Okay. Now, the way we design IR sensors is, so you know, in case of visible sensors, we have kind of standardized our design now. It's silicon based, few transistor pixel circuit, and we have made a fairly standard approach of designing them. In infrared, that has not been the case. It has also not been the case because there are different ways of measuring infrared, and there are large number of physics based things which happen here. So there is Seebeck effect, which essentially says if we have some materials which are at two different temperature and you connect a wire between them, you will see electrons will flow as an effect of the difference in temperature. Okay. There is pyroelectric effect, which says that if my temperature changes, that leads to a voltage in some materials, not all the materials for that matter. And there are parametric sensors which somehow manage to change voltage or current based on temperature based effects. These could be changing resistance based on temperature. Now we know most resistances are temperature dependent. Such sensors are called bolometers. They could be changing pressure. Such sensors are Golay cells. They could stretch a material, and there are many such. And even something as simple as the forward bias voltage of diode. Remember, you have done quite a lot of diode equations and transistor equations. Temperature always appears one way or other. If nothing else, Kt, where K is the Boltzmann constant and T is the temperature, appears at many locations. So wherever it appears, you know whatever my output of semiconductor material is going to be, it's going to be temperature dependent. So I can use that as a temperature sensor. So if nothing else, you take a diode, just design a simple diode, measure its current, that is a temperature sensor, if you can dissolve it into very small amounts. Does anyone remember the diode equation? How is it related to temperature? So the forward bias current is is e to the power KT something. That's what I said 5 minutes ago. You guys should be better than me, right? I did these courses 25 years ago. It's the I naught term which appears there. That is the heavily temperature dependent. Okay, so I naught times e to the power voltage something. There's actually, we will see it's not a very easy relationship with temperature. As a rough rule of thumb, we say for every 10 degrees Celsius it doubles. So it's an exponential kind of change, but that's a rough rule of thumb. It also depends upon what type of diode you have, what material you have made. Okay. So some of you might have seen things like this in mechanical engineering lectures, wherein we may use the Seebeck effect. Essentially, we use two different material and put one material in hot, one material in a cold place, and the other material is looking at your at your heat, and then most material will have some Seebeck coefficient. Here you have got alpha A. There was a pointer here which has disappeared. I can't move my mouse here. So alpha A minus alpha B, whatever is the temperature difference between these two materials will lead to a voltage being induced in the output line. Okay. Now generally the voltage produced by just one thermopile is quite small. So whenever you have one sensor producing a small response, there are 2 or 3 things which you can do. You can either put an amplifier after that, or you can try to increase the amount of response by putting sensors in series. So one is producing a small amount of volt. If I have n number of these, then I will get n times that voltage. Okay. So quite often we make series of these, particularly when we are making in chips. Now these sensors have been used for last 50 years, or if not 100 years. They are nothing new. What we are going to discuss is how do we put it on top of a silicon chip. So to do that, I mean, here are some examples of doing that. This is a micro electromechanical sensor chip, wherein you can see they have got a hot junction and a cold junction, and they are trying to keep these structures away from one another. And if you look at the literature, there are tons of such papers. Okay. Here's another example of this, wherein you have encapsulated your cold structure in a structure, and then you have made a 3D structure on top of that. I gave you these examples just to show in the micro electromechanical system world, people where they are trying to make smaller mechanical structures, and they have freedom of the kind of structure they do. There has been a large number of such sensors which have been built. But before that, let's try to figure out, so here we need 2 different type of material, right? One which has, and ideally it would be good because the voltage produced is the difference of their Seebeck coefficient times temperature. So ideally what we should make is these 2 materials having large differences of their Seebeck potential. Then I will get high voltage. And my apologies, now I am going to bore you with a table. So here are some materials which we have available in the CMOS process itself. I am making out of silicon. I have got polysilicon. I have got silicon on insulator, SOI. And then I can dope them with N-type or P-type. Okay. So doping then changes my Seebeck coefficient. So from here, I mean, you can see things like silicon on insulator has got fairly high Seebeck coefficient, but it's a bit negative. Polysilicon seems to be fairly good there, right? It's 190 units microvolt per Kelvin. And it's available. We made using polysilicon, we made the transistor. So I don't need to introduce a new material in my process. So other things like bismuth telluride, which are on top, they're not inherently available in a silicon process. Right? Even silicon on insulator means I have got an insulator base, then a dielectric, and then silicon. It's a costly process to make. So people used to make chips on things like silicon on sapphire or silicon on diamond. But polysilicon itself is available. So, I already have one material. Now, I need a second material. So, one I selected 190, the other would be good, either it has got 1000 or 1, right. Then I have got a good range, isn't it? So, here is the characteristic of some other materials here, and you can very well immediately see that metals, or at least some of the metals like aluminum or gold, have got very low Seebeck coefficient. So, if I already choose polysilicon with around 190, or if I can dope it nicely, I can also get slightly higher. The beauty of some of these metal is aluminum or gold is tricky to introduce in a CMOS foundry, because gold ions start diffusing in silicon and start changing the transistor properties. But yesterday when we were doing, at least those who were doing layout, they saw we had metals, metal 1, metal 2, metal 3. In most larger processes, we used to use aluminum as a metal to connect transistors. This is very interesting, because I already have polysilicon and I have aluminum, which means I can make such sensors on a classic silicon chip without introducing any other material. The whole crux of my course is, what can we do on a silicon chip? You can have fancy materials and we can add loads of these things. But if we take one beam of aluminum, other of polysilicon, we have got a thermopile kind sensor design. And there are a number of such commercial sensors in the market. So, you can go and have a look at these and you will find some things, a lot of these are there in the market there. The problem of these is twofold. One, you need to cool a junction or keep a junction cool, right. So, you need to shield it somehow from incoming heat. Classic sensors, in diode sensors, all the diodes were open, they were just receiving light. If my cold junction also gets hot, that will be not nice. So, quite often such sensors are made with one sensor on a chip. You are essentially looking at just the amount of heat, you are not looking at a particular radiation, you are not trying to take a heat map, you are trying to measure heat overall in the room. The other thing which is often designed is pyroelectric based sensors, and then you have got another property to look at for pyroelectricity. Okay. Here if you look at things like aluminum nitride, do we have aluminum nitride here? We don't, but you have got pyroelectric coefficients, if you look at the last column, of quite a lot of ceramics. Now, where do we use ceramics in silicon processes? So, till now we did not talk about how you package a chip. A chip comes packaged, and this is where we will be using quite a lot of other things. Now, people have tried making pyroelectric sensors from aluminum nitride, because again aluminum was available in silicon process, but it has not been a fairly good success because aluminum nitride itself has a very low pyroelectric effect. Doping it, something with scandium, making it a scandium aluminum nitride, that has been a fairly decent success, and people have tried making structures like this for, you have got a titanium, different electrodes, you have a sensing layer in between. So, trying to make a pyroelectric sensors on those kinds. The sensor which I believe has the most prominent use will be bolometers, and that is the one which I will be covering in a bit detail. So, the word bolometer comes from bole, which is Greek for beam of light, and these sensors work in a much simpler fashion. Essentially, their temperature their resistance changes with temperature, okay. And we have a temperature change coefficient which is 1 over RB delta RB times delta Ts. So, how much does my temperature change at a given, how much does my resistance change at a given resistance as my temperature changes? Now, this temperature coefficient of resistance for metals is positive, which means more temperature change, more does my resistance change. For semiconductors, I have written it negative. It is not purely negative, but in most room temperature, it is kind of negative. Why would you think the resistance of a semiconductor will reduce as I increase my temperature? Sorry? So, why is that not happening in metal? Metals also you have electrons which can move freely, right? So, one argument, yes, is higher the temperature, more energy electrons have, they can move faster. But then metal resistance should also fall down. But we know standard resistors, their resistance increases with temperature. So, the bottom line there is the more temperature you have, the more thermally generated electron hole pairs are being generated. In semiconductors, you have got larger number of charge carriers available to carry current. If more charge carriers come in, your native resistance falls down. Good. Now, look at the temperature coefficient of resistance for various metals and various semiconductors we have. Metals like aluminum and copper we have in the process, and they have very similar temperature coefficient of resistance. So, percentage change in temperature is fairly smallish. For semiconductors, we have got bigger changes here. Okay? And some semiconductors, something like gallium arsenide, they have got very good number compared to metal. Okay? Now, gallium arsenide is used for making a large number, not larger, but decent number of electronics, particularly high speed electronics. We use 3-5 semiconductors, though their use is reducing with time, but they are still there. Now, for some maths. We have done this lecture till now without maths, so some of you might be feeling a bit bored, right? So, we are now going to look at heat conduction equation. We have one mechanical engineering in house. You can explain this better than I can, right? You guys should have done thermo heat flow. And he's saying, nah, don't remind me of the bad days of looking at laws of thermodynamics, the 3 laws which still taught, isn't it? You guys were taught laws of thermodynamics. Sorry? So, you have forgotten it by the time you start MTech. The classic heat conduction equation is the one equation on top. There are few things to look at here. C is the heat capacity. Essentially, it is saying how much radiation is being converted to heat. Not all of that will be converted into heat. Okay? Next is thermal conductance. That is basically saying, so I have got a sensor and I have got my environment. What is the resistance between environment and me? It could be environment or it could be a heat sink, somewhere where heat is going. And last is, of course, the absorbed radiation power, and that is with an exponential attached to it. Now, this is a simple differential equation. It's the first order differential equation, right? So, all of you should be able to solve this. I am not going to bore you with solving this. You will get a relationship something like this. A delta T would become a function of incidence radiation, the conductance, and a time constant here. The time constant would be a fraction of your heat capacity and thermal conductance. Remember, we did lumped mass models where we looked at thermal effects as well. So, I will be talking in terms of electrical properties here. As temperature of the temperature of the sensor will rise with a rate of P incident by C. So, you see we have from this relationship you can come up with that. The limiting value would be a steady state value where it will plus some whatever is the incident radiation divided by my heat conductance. So, reach a steady state value in due course of time, and you might have seen as we start heating, we will reach at one point of time. Typically, if you have long cylindrical devices like wires, that is the kind of heat conductivity equation you have, which looks very similar to the resistive conductivity. So, what is the resistance of a cylindrical wire? Rho A by L. Sorry? So, rho L by A, right? So, L being the length of the conductor, area being the area of cross section. If you look at the conductivity, it will be 1 over R A by L. Electrical conductivity. So, the thermal conductivity has a similar formulation as the electrical conductivity. And of course, we define a constant here, which then tells us how it proceeds. Now, from there we could calculate the responsivity of the sensor, because we wanted to find what's that what's the temperature coefficient of resistance, and that comes out to be a fairly simple number where you have got G, which is in the denominator. Now, there is something else which one should remember when we have got a sensor whose temperature, whose resistance is changing with temperature. Now, generally we measure electrical sensors by passing a current through them. So, if my resistance is increasing, what is increasing? My voltage demand. Okay? Agreed? So, we said metal based sensors, their resistance increases with temperature, which in turn means my voltage demand is increasing. Now, if it increases to a very high value, I will need a very high voltage, or I will be having very high amount of power dissipation. So, this leads to a pole in the equation. Now, I am not going to do the equation for you, but think of it this way. If I pass the same current through the sensor, I have fixed my current, my resistance is constantly increasing, which means I am dissipating more and more power. So, at some point there is a risk I might burn out my device, I will be dissipating more heat. Now, semiconductor sensors, that is where they come nice, because their resistance is decreasing with temperature. So, I do not have to worry about this effect, or there will be too much heat which will be moving this thing. So, that is the relationship. So, 2 is the waveform which shows what happens to the voltage, what happens to metal based sensors, and then this is voltage by current. So, we are plotting the resistance here, okay, versus what happens to your semiconductor based sensors. So, you can see the power dissipation or the burnout effect in semiconductor based bolometers would be better than pure metal based bolometers. And that has been the trend as well. We are seeing more and more. Now, this is a very good trend. It plotted things like how are resistance based sensors working compared to diode based sensors. That is one. So, you, as said right in the beginning, you can use a simple diodes current also as a temperature sensor. So, if you just look at various sensors which have been proposed versus their pixel size. Now, why would we want to reduce the pixel size of sensors? Smaller is the size of the sensor, large number of sensors I can put on a chip. Now, bolometers are interesting because essentially you can do an array of bolometers. So, you can take an image. Little wonder diode based sensors, their size is reducing because you can make transistor processes in smaller and smaller geometry. But the other thing worth checking is, what was the size of the diode sensor which we took in while designing camera pixel? 3 micrometer by 3 micrometer. These are still significantly bigger than our camera pixel. We are looking at 20 micron, 60 micron, or that kind of sizes. So, while we can make an array, the individual pixel is still comparatively larger, which means the number of pixels which we will have is still fairly small. Now, earlier, this is how we were making our bolometers. Typically, you will have a metal absorber, my brain is dead today. And then you could design, if you're designing of amorphous silicon is, remember we looked at the temperature coefficient of resistance, silicon was fairly good. And we designed something like a 100 nanometer thick structure which is sandwiched between two dielectrics. So if you look in this structure, you have metal absorber on top, silicon dioxide are dielectrics. And in between we have amorphous silicon, which is a semiconductor, which is acting as a sensor. Or people were using some sort of vanadium oxide together with silicon nitride. Okay? And this is how you will be typically be making an IR absorber. So if you're making, say, here's an aluminum based thermistor, you will create long arrays of it, because you want as big an area as possible. The more the area it has, the more heat it will absorb. And making these fingered structures help you increase the area of the structure. And this also gives you longer length while keeping area of cross section small. A typical diode based bolometer would be something like this. You can see there's a PN junction there, and then you have an absorber layer, a heat absorber layer, which is to typically be made of metal. A number of these are not made in classic silicon processes. We use silicon on insulator processes. We want a good thermal material below which is not getting itself heated. We would want the sensor to be heated, not the package and not the substrate on which it is. Good. Then is the question of, so that was a sensor material which is less of an interest to us. We know we have material. How do we read it out of this? So we know a voltage is changing or current is changing, because the temperature is changing the resistance, which in turn will change my voltage or current. If I apply a fixed voltage, current will change. If I apply a fixed current, my voltage will change. So what kind of circuitry we have applied? So direct injection circuits are very similar to pixel circuits. So we designed a pixel circuit in the lab yesterday, right? We had a diode, few transistors. For bolometers, you can kind of design the same circuit. Right? You take the current produced by bolometer, integrate it on an external capacitor. Now, in case of image sensors, we are using diode as something which was measuring the current. Diode itself has a capacitance. So we are integrating that current on the diode capacitance. If we are using a bolometer based on another material, not a diode based ones, then you have to build an external capacitor to integrate that charge on it. Such devices can be made. They have been seen to have poor linearity and they are a bit noisy. A better solution could be not to measure. They're a bit noisy because now the capacitance which you have is coming in parallel with my bolometer. So whatever I am integrating is also affecting the bolometer operation. So one operation could be to buffer my sensor from rest of my electronics. And because it's a current based sensor, we can put a current mirror which hides the rest of the electronics with my sensor. I was going to cover the last topic, which is capacitive transimpedance amplifier. They work even better with bolometers. Basically, you are converting a capacitance into a voltage output. So this is an op-amp based circuit which you can build. Now you can immediately see why some of the reasons why our pixel is not becoming smaller. All these circuits consume a large number of transistors. So if you're making a transimpedance amplifier, that will be about 20 or 25 transistors. So you have 25 transistors, an array of 25 transistors, which inherent area will be bigger. So despite the fact bolometers can be made very nice and can be made smaller compared to others, the individual size is still struggling. We had a project in Glasgow where we tried to make a visible camera and infrared camera below that. So the idea being infrared has got energy which will pass through visible completely. So we make a camera below that so that it passes through the visible part. And we thought we can take the image and we can take the visible image as well as the infrared image at the same time. Two problems happened. One was we could make the visible pixel very, very small. So I'm taking the scene with say 1 megapixel, but I only have 10,000 infrared pixel. So how do I correlate the infrared part with the visible part? I mean, think of it this way. You take my picture, okay? A normal camera will tell you, the picture taken will be easy to identify where my nose is, where my ears are, where my eyes are. Because I have got tiny pixels, or the retina in my, not the retina, but you can see the eyebrows and the other things. But if your infrared pixel has got less resolution, maybe my whole eye is coming out to be 1 pixel. So finding boundaries becomes very tricky. How do we correlate these two? The other thing is the optical assembly. How do you make lenses for these, something which covers the whole broad spectrum? So as a sensor wise it works, but broadly speaking as a system wise we had difficulty. So right now most people will try to put two different sensors and try to take an image if you want to merge infrared and visible image together. It has been an active area of research because if you just look at a human being, I have an infrared profile and I have a visible profile. Right? So these two could give me some more information. If you go further high, if you look at terahertz sensors, then you can look at things which are just hidden below my skin or below my cloth. Some of these sensors are already there in the market. So if you go to some of the airports, you have these sensors which take a picture of you and then try to identify if you have got concealed things in your trouser, if you have concealed metal in your trouser, if you're carrying a gun or something. Okay? They haven't reached very deep internal objects. People are also looking at sensors which can look just below your skin to look at things like skin pigmentation to identify early signs of skin cancer. All of this comes from these sensors whose penetration depth is different. Right, we have been talking for an hour. By now I'm sure you are tired. So we'll take a 10-minute breather and then we'll come back. Okay? Sir? Can we stop the video recording? For the time being.